Hello everyone, let's talk today about safety standards and risk assessment in collaborative robotics. First of all, let's understand what a standard is. A good definition comes from the US Legal Dictionary, which tells us the following. Industry standards are a set of criteria within an industry relating to the standard functioning and carrying out of operations in their respective fields of production. In other words, it is the generally accepted requirements followed by the members of an industry. It provides an orderly and systematic formulation, adoption, or application of standards used in a particular industry or sector of the economy. They are used to help to create, grow, and stabilize markets. There are a number of standards organizations, national and international. The international ones are usually cited as ANSI or ISO, but there are a few other standard organizations. The ones that pertain us, robotics and collaborative robotics, are the ISO 10218.1 from 2006, which was the first one that calls explicitly for safety related to industrial robots development at the manufacturer level, establishing limits for force and power of industrial robots. Remember that collaborative robotics were only brought to light in around 2010, 2012 to be more precise. So the first standards for robotics pertained only the manufacturer level. So what are the standards for producing a robot? What would be the limits for force and power for a robot to be produced for the industry? In 2011 edition of this ISO, there were safety standards at the integration level. So given a robot and the way it's produced, what are the good practices of integrating a robot in a production line? And finally, in 2016, this is the most important standard for us. That's the 15066, which is the first safety standards for collaborative robotics. What it tells us, it defines the safety design features for a cobot and the requirements for applications. That is the first time the applications are considered in the robotic standards. And the requirements talk about the design and development of workspaces, lines of defense, speed and distances requirements to prevent accidents, and verification and validation requirements for the design and applications of cobots. So in these standards, there's a whole history of standards for robotics and collaborative robotics. These standards define as several different types of collaborative operations, which we have to take into account when we are designing a cell and when we are producing the risk assessment of a cell. If you want to know more about the standards, if you want to acquire the standards, you can do so by following this link. They are not cheap. I think each standard costs about $300. Well, this is not for us individuals to buy, it's for the industry to buy. So you can purchase, that's the link. You can purchase the new standard. There is a new standard 2020, which now includes requirements for mobile robots and a good first step towards ensuring the safety of human workers near industrial mobile robots. So for us, the cobot people in this cobot class, we are mostly interested in the collaborative robotics, in the manipulator robots that can work side by side with humans. The newer standards take care of autonomous robots, autonomous mobile robots, right? So if you want to acquire and if you want to develop a company on robotics, you should definitely buy all of these standards and be aware of these safety concerns and how to produce a safe cell. But in our ISO 15066, it talks about collaborative operations that are purposely defined robots that work in direct cooperation with a human within a defined workspace. That is the definition of collaborative operation. And also they define a collaborative workspace. So you have to take into account the risk assessment of the operation and the workspace and at the design stage. So a workspace within the safeguard space where the robot and human can perform tasks simultaneously during production operation. So the safety for collaborative robotics, you have to take into account specific design factors that help the robot arm to be safer for human interaction. So this is obviously important if we want to have humans working side by side with robots. That's what we want. The reason is that humans are very good at creativity and problem solving, whereas robots are excellent at precision and repetitive tasks. So the ideal industry, modern industry, what they call part of the industry 4.0, is that we get the best of both worlds. We get the strength of humans combined with the strength of robots, and in order to do that, you need collaborative cells. But in order to have a safe collaborative cell, you have to follow a number of factors in the design of the collaborative robot system, such as what kind of function? How would the robot and operator be working together? There are a few different kinds of operations. One of them is coexistence, where robot and operator are in separate spaces. Usually in the coexistence workspace, the robots operate inside cages, and the robot turns off when a human enters its workspace. It could be a cooperative coexistence, where both human and robots use the same workspace, but at distinct times. So for example, if a human needs to load parts for the robot to manipulate, so the robot will be off, the human will get close to the robot, put the pieces near to the robot, press a button, and the robot will work on the pieces that were put in front of it. So there is no need for cages. Or full collaboration, which both humans and robots use the same workspace at the same time. And this can only function with strict restrictions of force, speed, and movement for the robot, for the safety of a human. In a full collaborative workspace, there is potential contact between the operator and a robot. That could be either intended, accidental, or due to failure. In order to produce your risk assessment and to construct a safe work cell, you have to take into account two kinds of contacts. One is quasi-static, where the operator's body part can clamp between the moving part of the robot and another fixed or moving part of the robot system. You have to really be aware of what we call pinch points, where you can get your hand or your arm or even other parts of your body trapped between the moving robot and other fixed part. And another kind of contact is transient. Transient is a momentarily where the operator can quickly retract or recoil from the moving part of the robot system. Let's see a little video from our colleagues at UR. Well, I said that they produce quite a good number of educational material for cobots. Let's see what they talk about these issues here.
In this video, you will learn how to calculate a pressure applied by a robot. Calculating a pressure is simple physics. First, you need to know the maximum force the robot is applying in a particular directions. We usually rely on the force setting of the robot. For example, this robot is limited to 150 Newton. You need to know the area of contact of the potential impact. First, measure the area. In this case, the area is 2 cm by 1.5 cm, which means a 3 square centimeter area. For a more complex geometry, other calculations should be used. The pressure is in Newton per square centimeters. So by dividing the value in Newton by the value in square centimeter, you obtain the pressure value. For this example, the pressure is 50 Newton per square centimeter. According to the ISO TS 15066, this pressure is acceptable. To avoid to reach the pain level, you may want to increase the area or to limit the force applied by the robot. Stay tuned for our next video on how to evaluate a risk.
Okay, so this video was about calculating pressure, and this is the big video that explains transient and quasi-static impact.
Here at Robotic, we know that collaborative robot safety is a huge concern for our customers. This is why we want to explain a couple of basic safety concepts using collaborative robots. In this first video, we will talk about the difference between a quasi-static and a transient impact. A transient impact occurs when the robot hits you while nothing is holding you. In other words, you're able to move freely when the impact occurs. A quasi-static contact happens when the robot crushes you against a fixed object. To perform your risk assessment correctly, you need to consider that the pain level for a transient impact is 2 times higher than a quasi-static impact. According to ISO TS 15066, the pain threshold for N is 135 Newton for a quasi-static impact and 270 for a transient impact. This small difference can make a big difference in your risk assessment process. Stay tuned for our next video on how to calculate pressure due to an impact.
Alright, so now you understand transient and quasi-static impact and how to calculate pressure. Both important concepts for you to create your risk assessment. So you have to take into account, as I said, the possible contact scenarios and take into account the pain levels for risk assessment. We're going to see that there are tables for the pain levels for distinct parts of the body. What the guy in the previous video said, that he just produced one single value, but there are actually different values for different pain levels in the body. So obviously the head can has to be can't get much of the pain, right? Or that's different from a hand or an arm, right? So the general rule is that in a transient impact, as I said, the force can be applied that is 2 times higher than the quasi-static impact in, as I said, in all critical parts of the body. And this risk assessment should be done when projecting a cell, and once the cell is completed, you have to run the risk assessment again and mitigate any potential risks. So this is the table that I mentioned before. This is part of the 15606 standard. So as I said, there's a body region, so skull and forehead are considered obviously critical zones, and they are divided into specific parts: middle of forehead, temple, and masticatory muscle. And in a quasi-static contact, where the body part is trapped between a moving part of the robot and something fixed, there is a maximum pressure, maximum permissible pressure of a certain value that's 130 newtons per centimeter square, and a maximum permissible force of 130 newtons. Whereas in this is the part of the middle of forehead and temple. In the masticatory muscle, the force is only 65 permissible. It's not that you're going to have your robot to hit somebody's head. Actually, you don't want that to happen, but if that happens, this should be the maximum amount of force that the robot can take at that particular area. So meaning that once you're projecting your cell, you expect the robot, for instance, to walk around the person's arms. But if for some reason the robot reaches the height of the person's skull, the force should be reduced. So you should project yourself such that if the robot reaches a particular height, the force will be reduced. And of course, in a transient contact, there is no multiplicatory factor. So this for this part of the body region, the critical part, there is only one value for quasi-static contact and transient contact. Now in the neck, you can apply the transient contact in the project of your cell. So the maximum permissible pressure, let's talk about force. There's obviously a relation between pressure and force, as you saw in the other video. So maximum force is 150 for a quasi-static contact, but from a transient contact, a person can take up to 300 newtons. Back and shoulders, for a quasi-static contact force, the permissible impact when it happens, you don't want it to happen, you don't want it to happen, but if it happens, it has to be 210, and for the transient contact is 2 times s, 420, and so on and so forth. Same thing for chest, abdomen, pelvis, upper arms, and elbows. You've seen this video, the pressure is simply a force spread on a surface. The larger the area, the less the pressure. So if the force is applied on the tip of a needle, the pressure will be very high and will probably overshoot the collaborative robot standard recommendation. So how do you mitigate this? You mitigate that by enlarging the area where the force is applied. So you can't change the tip. You're going to have to change your application. If your application has a needle point, then it's not a collaborative application, right? So you can't have a human working side by side with a robot holding a knife. So it's not a collaborative application. It goes more towards a more traditional robotics where you have to engage your robot or do one of the other less collaborative operations such as coexistence or cooperation. So that's certainly a robot holding a knife or a needle is not a collaborative robotic system. Remembering that system is robot plus application. And the application includes the tool point, right? Where was I? Say, okay, force. If the pressure is above the standard, you should limit it in the cell design. How you can limit? You can either, as I said, increase the area, changing the tool point, or limiting the force applied by the robot. You have all of these, you have the control of the robot, right? It's fully programmable, and you have all of the settings of the robot, the force and speed. If you want to know more about this ISO 15066, there's this booklet. This booklet is free. And it's to tell you the truth, it's not very good. It's making a lot of propaganda about robotic A, but it does explain some of the major points in the ISO 15066. But if you, again, as I said, if you want to build a company that works with robotic cells, either designing it or selling, you should actually acquire the ISO and the proper standards for your application. Now, this standard has a number of collaborative operation requirements. Some of them are, the most important of them are safety rated monitored stop, hand guiding, speed and separation monitoring, power and force limiting by inherent design or control. These are all strategies that you can use in order to build your robotic cell. So in a safety rated monitored stop, a stop is assured while maintaining power to the robot. The operator may still interact with the robot, but the automatic operation may resume when the human leaves the collaborative workspace. Now, in this case, this is not collaborative. This is what we called here cooperation. It's the same workspace, but at distinct times. The human gets closer to the robot cell. The robot stops and waits for the human to leave the cell. Let's see a video of a safety-rated monitored stop. All right, so this is one of the strategies. The other one is hand guiding. Hand guiding, in a hand guiding situation, the operator is in direct contact with the robot and is using hand controls to direct the robot where to go and what to do. The robot systems under manual control. Both the person and the robot may move at the same time, where the motion is controlled by the robot. Let's see this hand guiding strategy for your cell. So an example from
FANUC's new CR35IA is the first collaborative robot in the industry to feature a heavy 35 kilogram payload while being ISO certified to work safely alongside humans without the need for fencing. Another first from FANUC is the CR35IA Collaborative Robot's Hand Guidance feature. This unique feature allows an operator to safely control and guide the robot arm and tooling, providing collaborative effort between the robot's strength and the operator's finesse. Typically, a robot is jogged or moved with a robot pendant. However, collaborative robot hand guidance from FANUC enables the operator to show the robot where to go without the pendant, and can be used to teach the robot points or a path. The FANUC CR35IA collaborative robot was developed to help manufacturers solve ergonomic challenges by handling applications that are physically demanding for humans, such as repetitive heavy lifting. To learn more about FANUC's collaborative robot, please visit robot.fanucamerica.com.
Now, this is different from programming the robot. The narrator mentioned programming the robot, but what hand guiding is that the robot is there operating, doing its robotic thing, and you go there as a human and interfere with what the robot is doing and change the way it's doing. So this is an actual collaborative behavior. You saw in the video that the robot moved very slowly, and once the human touched the robot, it just stopped. So this is force feedback. This is the major issue in collaborative robotics, and one that it's company secret. Each company has its own way of doing this force feedback loop in collaborative robotics. Okay, next is a speed and separation monitoring. The robot speed is reduced the closer an operator is to the hazard area. There is a protective stop is issued when the operator is in potential contact. Person and robot can move at the same time. Let's see a video of this happening. This video has no sound, so the robot is operating here. Let's see if I can move when the operator comes. Here, the operator comes. The robot is interacting with the operator. So you see that it's not actually, hitting the operator. It has sensors that prevents the robot from colliding with the operator. In the you see that there are mode operators, so it's reduced stop. The robot stops when the operator gets into the critical area. and if the robot operator is not in the critical area, the robot just reduces its speed. It's what they call it. Oh, yeah, here the robot stopped. This is a quite nice video. It shows this kind of operation, this kind of strategy called speed and separation monitoring. Right, let's move on to now. So that's a few more steps to consider. Power and force limiting. You can limit the speed, torque, motion of the robot. Control so that you can reduce any potential contact between robot and operator. Since in a work cell, in a collaborative work cell, contact is permitted, but it must be controlled and its risks understood. That is the reason for doing the risk assessment that we're going to see in a few minutes. Person and robot can move at the same time. Possible risk reduction measures. We can change the robot design, such as with rounded shape and compliant materials. Appropriate application selection in robot cells. So the end effector is very important. The workpiece is very important. The motion part is very important. As I said, a robot holding a knife or a sword is not a collaborative robot, because I should say robotic system, because the system involves a robot plus application. You should take into account when there is transient contact and when there is quasi-static contact, and how you mitigate them or how you control them if there is no way of avoiding contact. Steps to consider: if you are building a cell, know your standards, by your standards, think in terms of the whole system, as I said 100 times, robot plus tool plus object, select the adequate equipment, do the risk assessment, we are going to see in a minute, and mind your surroundings, be aware of the robots and locations at all time, avoid positions or paths that might cause contact with face, head, neck, clamping or pitching. In the end, you can do the best risk assessment, but the one at risk is you as operator. For more information, you can go to the RIA, Robotic Industries Association. There's a bunch of information, and as I said, this is manual by Robotic. And let's take 5 minutes to talk about risk assessment. We talked about potential risks, and how you can do what you can do with your cell to mitigate these risks. But in order to know what is the risk of your cell, you have to do the assessment, where you identify hazards, you mitigate risks, and you document the whole process. And this is a responsibility of the entire team, because the entire team should be aware about the risks involved in a collaborative cell. Let's see a brief video introducing risk assessment from Robotic again.
In a risk assessment process, it is important to identify the different risks involved in the use of a collaborative robot. Evaluating a risk correctly can be a game changer in your risk assessment process. The risk is usually evaluated using 4 different criteria: severity of injury, possibility of occurrence, possibility of avoidance, and frequency of exposure. Let's take the simple example of a gripper hitting my hand against the table. The severity of injury is rated from 0.25 to 65, the lowest being a scratch or a bruise, the highest being catastrophic. In this case, the pain level is not even reached when the robot stops, so a rating of 0.25 is accorded to this risk. The second criterion is the possibility of occurrence of the hazard. It is rated from 0.05 being almost impossible to 6 being certain. In this case, we consider that this risk is possible. The third criterion is possibility of avoidance, rated from possible being 0.75 to impossible being 5. In this case, the robot is not moving fast enough to crush me instantly, so it is possible to avoid the impact. Finally, the frequency of exposure is rated from 0.5 being annually to 5 being constantly. In this case, the worker is exposed daily to the hazard. Then, all these criteria are multiplied together to give a certain rate. In this case, 1.4, which is considered as being neglectable. Once all your risks are evaluated, you can do a risk reduction process, starting with the most dangerous one. Stay tuned to see other videos on collaborative robot safety.
Right, so just to put into slides what he said, there are 4 criteria for risk assessment: severity of injury, SI, that runs from .25 to 65, where .25 is the minimum severity, and 65 is very severe. Possibility of occurrence, that's 0.05 to 6. Possibility of avoidance, 0.75 to 5. Frequency of exposure, 0.5 to 5. In the rating, you multiply all of these criteria. So, severity of injury, SI, it's a qualitative measure, right? So you can it can be classified as serious. It's normally a non-reversible injury. Likely, the person will not return to the same job after recovery from incident. Or there will be either a fatality, a limb amputation, a long-term disability, a chronic illness. If any of the above are applicable, the rating is serious. Can be moderate, normally reversible. Likely, the person will return to the same job after recovery. That it includes broken bones, severe laceration, short hospitalization, short-term disability, lost time, multiple days of work, fingertip amputation, not done. If any of the above are applicable, the rating is moderate. And minor, there will just be, a first aid, no recovery required before returning to job. That includes bruising, small cuts, no loss of time. It does not require attention by a medical doctor. Exposure can be high or low. Typically, high is more than once per hour. Frequent or multiple short durations, situations which could lead to task creep and does not include teach the robot. If any of the above are applicable, the rating is high. And low, typically less than once per day or shift, occasional short durations. And avoidance, that's avoidance is based on the clearance distance and reaction time. That is not possible to avoid, where there is insufficient clearance to move out of the way. The robot system layout causes the operator to be trapped with the escape route towards the hazard. Safeguarding is not expected to offer protection from the process hazard. Not likely, insufficient clearance to move out of the way and safety-rated reduced speed control is used. Obstructed path to move to safe area. Hazards moving faster than reduced speed. Inadequate warning, reaction time. Might not perceive the hazard exists. Or, very likely, sufficient clearance to move out of the way. Hazard is incapable of moving greater than reduced speed. Adequate warning, reaction time. Positioned in a safe location away from the hazard. So you want actually the avoidance to be likely for any potential risks in your robot. And you apply the risk level matrix, where you're going to evaluate every one of your 3 factors: severity of injury, exposure to hazard, and avoidance of hazard. And you want all to get to risk level negligible. So for instance, you want the severity of injury to be minor, the exposure to hazard to be prevented or low, and the avoidance of the hazard to be likely. Then you're going to get a negligible risk level. A low is also possible and also allowed by the standard, where you may have a moderate severity of injury and a low exposure to hazard. You fall into medium. You have to avoid any high, or it's definitely very high classification in your risk level matrix. So these are actually 2 ways of doing your risk assessment. You can either do the risk level matrix, or you can do the rating, multiplying. The classes are the same. It's just a different way of doing your decision, of taking your decision about your matrix, about your robotic cell. And obviously, you want to eliminate your risk. You have to use the risk reduction measures where you either eliminate the risk or substitute or limit the interaction, or in the end safeguarding, changing the speeds of the robot, or putting the robot, or changing the way the robot operates with a human. That could be coexistence instead of actual collaboration. Or you can use complementary protective measures, warnings and awareness. And usually it's good to have a combination of all of these factors, of these risk reduction measures, risk mitigation measures, to change a risk level from very high and high, or even medium, to low and negligible. And low and negligible are risk levels that are allowed by the standard, by the current robotic standard. So how you do a risk assessment? You should prepare for and set limits of the assessment. You should understand the intended use of the robot, the application, the authorized personnel, the process flow, and the limits, force limits and speed limits. Identify the tasks and potential hazards. Quantify the initial risk using the risk scoring system. Once you quantify the risk, you do a risk mitigation process. You reduce risk by a number of techniques that you can use, as I mentioned briefly here. And after that, you assess residual risk. And if there is still considerable risk in your risk assessment, you have to repeat number 2 to 5 until the residual risk is acceptable, and document the whole process. Right? Potential causes of injuries are obviously unauthorized access, plus people that don't know how to handle a robot and don't know what the robot's doing. Fault in control system, that's one of the most common causes of hazards. Mechanical failures, in the electrical power failure, there is risk of electrical shock hazard. Inadequate installation, that is the task of the engineer to verify that. Good design is essential. Use the appropriate robot for the appropriate application. I supervise students in the work placement, especially related to robotics, industrial robotics. And there is one thing that the first question that I ask is that, where is your installation? Is it adequate? Is it using the appropriate robot? Is the design fit for risk mitigation? Yeah, that is essential. Of course, mechanical failures, electrical failures, and fault in the control systems are difficult to control, but this is our task, right? To provide an adequate installation. This is the task of robot engineers and technicians. And that's all, folks. We're going to be dealing with risk assessment. We're going to be doing one risk assessment in the workshops next week. And looking forward to it. I'll see you there. Thank you.